We're going to continue discussing the Allais paradox, now a somewhat different version. And I put up figure 2.4.1 of the book, where the panels E and F of that figure. We've seen it before. First, I indicate the majority preference. I indicate bars, the things that are not preferred. So in the left figure E, the lower prospect is preferred. People rather have the 10 million for sure. Figure F, the upper prospect is preferred. That's how the majority preferences are indicated here. Now, we have already seen as homework that expected utility cannot accommodate these preferences. They are violating expected utility. So let's not look into that. Let's immediately go to how, of course, rank-dependent utility can accommodate these preferences. Let's immediately go into that. Now, I wanted you to show it, but a bit differently than the previous slide. Now, I want to do quantitative work. I want you to really write the weighting function and utility. Well, we're going to focus on the novelty of rank-dependent utility, the weighting function. So we'll take utility linear. With that understood, I ask you, write the weighting function. What kind of weighting function, what values really give these preferences? So that with that weighting function in the left figure, the lower prospect has a higher rank-dependent utility than the upper prospect. That's what I want you to do. Now you can pause the video for a while, work on it until you're done, and then come back. Okay, I assume you worked on it as much as you like. So now I will show you the solution as I do it, as I can solve it. And first I look at figure E. The rank-dependent utility value of the upper prospect is W of 0.8 times, I don't write a million, times 50. You know, that's the best outcome, so I take it first. The zero outcome is 0, I don't write it. This is smaller than the rank-dependent utility of the lower prospect. That is probability 1. So weight 1 goes to the outcome 10. I don't write million. So we get that inequality. I rewrite W of 0.8 must be less than 1 over 5. Now I go to figure F, and I get the rank-dependent utility of the upper prospect is W 0.04 times 50. Again, I don't write the million. That must exceed the rank-dependent utility of lower prospect, W 0.05 times 10, and I'm not writing the zeros, of course. That means that I can rewrite the ratio of the probability weighting function that we have here should be W 0.04 over W 0.05 should exceed 1 over 5. So that's what we get. Now, it's quite easy. These conditions are necessary and sufficient for the preferences to hold, and it's, of course, very easy to make any probability weighting function simply satisfying these two conditions. Very easy to do. So let me show you a graph, one way to do it. So the first thing is that we're going to look at probability 0.8. There, it must be below 1 over 5. So here's the level 1 over 5. I can just take any point there below 0.2 and then I'm fine. And friends, the whole shape can be like this. Well, we also should reckon with this second inequality, but that second inequality is very easy to accommodate. For instance, if W is linear in the region, as I did it here, then that ratio is 4 over 5. So it by far exceeds 1 over 5. So we're fine there. This curve very easily accommodates the finding. Well, I told you already in the previous recording that Allais paradox has to do with the certainty effect, that people over-appreciate certainty, so to say. They have strong preference for it. And that it can be seen that has to do with the weighting function steeply going down at probability 0.1. So that probability P is 0.1 is evaluated much higher than everything that comes below it. And this curve is showing that. So that has to do with certainty effect that's going on in Allais paradox. Other than that, the curve is not very realistic empirically. At this moment, I'm not doing much yet to get empirical realism. I just want to show you how in theory it is possible to use rank dependent to capture all kinds of phenomena. Empirically, more realistic is to assume that utility is very concave for these extreme amounts of money. Then one model, the shape of the weighting function that we have here is not really, it's too extreme. But then you can get more realistic shapes of probability weighting function. We'll see many cases of that soon to come. They, in combination with concave utility, can also accommodate the Allais paradox in an empirically realistic manner. So that can also be done, but that we leave for future presentations. So I'm stopping here this recording now.